This is day 2 of section 6.2, and the concentration today is going to be on combining random variables. So for any two random variables, x and y, t is equal to x plus y, and the expected value is E of t is equal to mu sub t equals mu sub x plus mu sub y. In general, the mean of the sum of several random variables is the sum of their means. All right, a couple of notation issues here. You have to be careful with your labeling. We have three means in the same equation. This is the mean of the first distribution, the mean of the second distribution. This is the mean of the sum of those two, or t usually for considered total distribution. So you need to make sure that you're clear. You can't have mu is equal to mu plus mu without indicating what's what. So pay attention to those subscripts. Okay, what about the variability? In order to address variability, we must consider the independence of the variables. Okay, knowing whether any event involving x alone has occurred tells us nothing about the occurrence of any event involving y alone, and vice versa, then x and y are independent random variables. Probability models often assume independence when the random variables describe outcomes that appear unrelated to each other. You should always ask whether the assumption of independence seems reasonable. Okay. We are revisiting our friends at EDCC, El Dorado Community College. El Dorado Community College considers a student to be full-time if he or she is taking between 12 and 18 units. The number of units X that a randomly selected El Dorado Community College full-time student is taking in the fall semester is the following distribution. Okay, so we saw this in yesterday's lesson, and we have our summary statistics. We have the mean, the variance, and the standard deviation. Okay, new to today, EDCC also has a campus downtown specializing in just a few fields of study. Full-time students at the downtown campus take only three unit classes. Let Y equal the number of units taken in the fall semester by a randomly selected full-time student at the downtown campus. So here the possibilities of the credits or the units you take are only 12, 15, 18. All right, they're giving us the mean, they're giving us the variance, they're giving us the standard deviation. If they didn't tell us those things, we would do the same thing we've been doing for the last couple of classes. He's going L1, he's going L2. You run your one variable statistics, L1 for the X values, L2 for the frequency. The calculator tells you the mean, the standard deviation. Square this in order to get the variance. Make sure you have the appropriate symbols for each one of those guys. Okay, back to the problem at hand. If you were to randomly select one full-time student from the main campus and one full-time student from the downtown campus and add their number of units, the expected value of the sum would be. So we have distribution X already defined. We have distribution Y already defined. These two guys here. S is going to be adding those two things together. From the last slide, we know that the mean of the sum is just going to be the sum of the means. Okay, general details in terms of importance of getting full credit by AP rubrics. Blank formula, numbers plugged in, final answer, and this really should have a unit, in this case units or credits. All right, now let's address variability. Let S equals X plus Y as before. It is reasonable to assume that X and Y are independent because each student was selected at random. Well, that's kind of a cheesy example, selected at random from two different campuses. So knowledge about one person doesn't give us any knowledge about, knowledge of one person on one campus doesn't give us any knowledge about a person on another campus. For two independent random variables, and that independent is very important, X and Y, if t is equal to X plus Y, then the variance of t is the sum of the two individual variances. In general, the variance of the sum of several independent random variables is the sum of their variances. Okay, remember, you can add variances only if the two random variables are independent, and you can never add standard deviations. So here's the deal. Standard deviation in general for describing a data distribution or a probability distribution is a much more convenient, applicable, easy to deal with, very informative summary statistic to have. But there are certain mathematical operations that cannot be done with with standard deviations. That's why we want to know variances. You can add variances. You can't add standard deviations. So although the 9.961 as the variance for the sum of two variables doesn't tell us a whole lot, we need to get that in order to get the standard deviation. All right, back to our community college. Let B equal the amount of money spent on books in the fall semester for a randomly selected full-time student at El Dorado Community College. Suppose that mu sub B is equal to 151, standard deviation is 32. So the mean amount spent on books is 151, standard deviation of $32. Recall from earlier that C is equal to the overall cost for tuition for a randomly selected full-time student at El Dorado Community College, and those are summary statistics from our work from yesterday. Find the mean and standard deviation of the cost of tuition, fees, and books. C plus B for a randomly selected full-time student at community college, at El Dorado Community College. So the mean of the sum is the sum of the means. Okay, you can always add means regardless if your two variables are independent or not. That's always valid. But when it comes to the spread, number one, you can never add standard deviations. You can add variances if the independence assumption is met. Okay, the standard deviation cannot be calculated because the cost for tuition and fees and the cost from books are not independent. Students who take more units will typically have to buy more books. So knowledge of one thing gives us information about the other. If the variables were independent, we would add the variances, then take the square root for standard deviation. Standard deviations never add. Earlier, we defined X is equal to number of units for a randomly selected full-time student at the main campus. Y was the number of units for a randomly selected full-time student at the downtown campus. So, the mean for the full-time campus, for the main campus, 14.65 units, standard deviation of 2.06 units with our variance. For the other campus, 15 units, standard deviation of 2.32 with that variance. At the main campus, full-time students pay $50 per unit. At the downtown campus, full-time students pay $55 per unit. Calculate the mean and standard deviation for the total amount of tuition for a randomly selected full-time student at the main campus and for a randomly selected full-time student at the downtown campus. So from earlier, T is the total amount collected from a random full-time student at the main campus with that standard deviation. Okay, let U equal the amount collected from a randomly selected full-time student at the downtown campus. So the $55 per credit times the average number of credits is $825. The standard deviation affected by multiplication but not addition or subtraction. So 55 times the standard deviation for that is the 1.26.50. So we can add the means. We can never add standard deviations. We can add variances as long as we can make the independence assumption. Because the students were randomly selected, well, I think that's a little bit cheesy. Randomly selected from two different campuses is kind of more of the valid thing. T and U are independent random variables. So that means we can add the variances. So we know the standard deviation, square to get variance. No standard deviation, square to get variance. Get that number, square root back to standard deviation. So that's the mean and the standard deviation for that sum of two random variables. And I guess, units. You should always have units. For mean, you should always have units for standard deviation, in this case dollars. The unit for variance would be squared dollars. Squared dollars, it's kind of tough to wrap your brain around why you even want to report that. Again, variance is something that we use for computational purposes, not really to report final summary statistics. All right, well, what's the deal if we subtract variables instead of add variables? What's the same and what changes? So what happens when we define a random variable as a difference of two random variables? In summary, we find the following. For any two random variables, x and y, the d in this case they're using for difference, x minus y, then the expected value is. So if you're subtracting two random variables, the mean of the difference is just the difference of the means. In general, the mean of the difference of several random variables is the difference in the mean, so I just said that. And the order of subtraction is important. The order of subtraction is important in most situations. I don't know if it's addressed on a later slide or not, but I want to emphasize it here. We could always add means regardless if the variables were independent or not. You can always subtract means regardless if the variables are independent or not. Okay. What about variance? For any two random variables x and y, d is equal to x minus y, then the variance of d is. Okay. In general, the variance of difference of two independent random variables is the sum of the variances. All right, so these guys need to be independent. Okay. As long as they are independent, then we can deal with the variances, and whether this is an addition or subtraction, this is always an addition. And exactly why that is what it is goes a little bit beyond the scope of our particular curriculum. This is just take the word of it, the authors, that this is the case. All right, so a subtraction example. Earlier we defined T is equal to the amount collected from a randomly selected full-time student at the main campus. U is the amount collected from a randomly selected full-time student at the downtown campus. Okay, so mean for the main campus, standard deviation for the main campus. Downtown, downtown. Suppose we randomly select one full-time student from each of the two campuses. What are the mean and standard deviation and the difference of tuition charges? T minus U. Okay, subtraction is important, so make sure that you follow that when you set up the problem. Interpret each of these values. So, the mean of the difference is the difference of the means. U sub T minus mu sub U and negative 9250. Okay, interpreting that. That means, on average, full-time students at the main campus pay $92.50 less in tuition than the students at the downtown campus. All right, because the students were randomly selected, we'll randomly select it again from two different campuses. A little bit more of a thorough explanation. They are independent. Okay, if we are subtracting means, we can add variances, assuming that the independence condition is met. We can always add or subtract means regardless of independence. In order to add the variances, whether that's an addition or subtraction, we have to have the independence assumption being met. So we add the variances, take the square root, and that gives us the standard deviation. Okay, although the average difference in tuition for the two campuses is negative $92.50, the difference in tuition for a randomly selected full-time student in each college will vary typically from the average difference by about $163. Right, one more example for today. Again, in terms of the structure of our typical lesson, everything that we've done so far has been dealing with, so far this lesson has been dealing with discrete random variables. Now what about a continuous one? And most of the continuous ones we're doing in this part of the book are going to be normal distributions. Okay, if a random variable is normally distributed, we can use its mean and standard deviation to compute probabilities. Okay, we knew that. Any sum or difference of independent random normal random variables is also normally distributed. Okay, that's new, and that's important. So, if we have two normal variables, and we add or subtract, and we looked at both scenarios in terms of how the computations play out, in addition to what we've talked about, if they're independent, we know that the sum or difference is also going to be independent. I'm sorry, if we know that they're independent, the sum or difference will also be normal. Okay, suppose that a certain variety of apples have weights that follow a normal distribution with a mean of 9 ounces and a standard deviation of 1.5. If a bag of apples is filled by randomly selecting 12 apples, what is the probability that the sum of the weights of the 12 apples is less than 100 ounces? So, X is going to represent the weight of a randomly selected apple. So X sub 1 is the weight of the first apple, X sub 2 is the weight of the second apple, so forth and so on. So we're interested in the total weight, T, X sub 1 plus X sub 2 plus all the way up to X sub 12. So the new distribution is the sum of 12 individual distributions. Each individual apple has its own distribution, and we're making a new one, adding them all together. So if the apples are randomly selected, that means that we can reasonably assume that we have independence. So because T is a sum of 12 independent normal random variables, T follows a normal distribution. So because we're dealing with normal random variables, and we can assume them, or we do assume them to be independent, that means the sum or difference will also be normal. Now, as far as the mean and standard deviation for this distribution goes, the mu of the total distribution, you can always add or subtract means. We didn't even have to have the normal condition for that. 9 plus 9 plus 9 plus 9, blah, 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 for 108 ounces. We can never add or subtract standard deviations, but as long as that independence assumption is met, we can add variances. So 1.5, when you square it, is 1.52. So it's 1.52 plus 1.52, blah, 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 all the way up to 27. And then once we have that, we can square root to get back to standard deviation. So now the probability question. What is the probability that the sum of the weights of the 12 apples is less than 100 ounces? So what's the probability that T is less than 100? Lower, upper, mean from here, standard deviation from here, gives us the area. There's about a 6.2% chance that 12 randomly selected apples will have a total weight of less than 100 ounces. Okay, AP rubric note. This is a pretty common structure of a question where you're given an initial distribution, there's some kind of transformation going on or combination, you have a new mean and standard deviation, and then you have to use that to answer a probability question. As long as these numbers are reasonable and you use reasonable numbers here, you're typically not going to get charged double jeopardy if there's a mistake here. Like if you made an error here and that was like 100 instead of 108, and you use that number here and everything else is good, you'll lose partial credit for this part, but you won't lose credit for that part. If you get a number here that obviously makes no sense whatsoever at all, and you use a number that obviously makes no sense whatsoever at all in a future calculation, then you're probably going to get double jeopardy, because you don't understand what these numbers should be in terms of, like, you have, a negative 108 ounces. How's the mean possibly negative 108? You use a negative 108 here, they're not going to give you credit even if you did this correctly with that wrong number. All right, I think that wraps it up for what we're covering in 6.2 for today.